Hello teammates, this is Mr. Nanini coming to you from the physics bunker. You're going to be watching this on the 17th of April. And we've got one problem today. We're on page 166. Number 1, we're going to sharpen up the prudent pencil of physics. Look at that. You could do surgery with this. So I was thinking about modifying this problem, and I don't want you to be confused, but I think this is a good lesson. And so let's read carefully. So National Academy of Sciences, real organization, they're going to map deforestation, and they're going to put a satellite in polar orbit. What that means is it's going to orbit instead of around the equator, it's going to orbit around the poles. And it's another way of covering the Earth with imagery. So we're given the radius of the Earth, and we're told this. So we're told it's going to be 160 kilometers above the surface of the Earth, and we're told that the acceleration of gravity at that altitude is nearly the same as it is at the surface. So if in your physics careers you run across something like that, that's inviting you to use we're going to use 10 meters second. And I thought about modifying this so I don't confuse you, but I think it's good. Because I think the more limber your neurons are, the more you're going to be able to contribute to getting this world of ours back on the track. So we're going to use that where we've got the radius of the Earth, altitude of the satellite, mass of the satellite, which we're really not going to need. Really not going to need that. Construct a diagram for the satellite. So if this be the Earth, this would be the satellite. And the satellite's going to be in polar orbit. So let's polar orbit. So we have the satellite coming around the Earth like that. If that's the poles. Imagine this is over the top, that's over the bottom. That's not important. Key parameters. We know that the satellite and the Earth are Newton's third law of force pair. We've got an acceleration, don't we? We're told we can use what it is at the Earth's surface. And we know that. We don't know the velocity yet. We're going to want the velocity. Distances we have. And I want to show you something because I think this is a good math skill. So we know we don't use kilometers. So we're going to convert that to meters. 6.38 times 10 to the 6th meters. We're given the altitude, and we can't use that either, can we? We want that to be in meters. So we're going to modify that to, so 160 kilometers times 1,000 meters per kilometer is going to give us 160,000 meters. And we're going to convert that. Let's convert that to scientific notation. 1.6 times 10 to the 1,2,3,4,5 meters. Now watch this. You can do this without your calculator. And I think your neurons are going to appreciate this. So we can convert, we can't add those directly like that, can we? But we can convert this to 0.16 times 10 to the 6th meters, can't we? So we move that decimal place here. We're going to account for it there. And if you don't believe me, it's okay. Check it out in your calculator. Now look at what we can do. We can add these 1.16 times 10 to the 6 meters. We're going to add those 8, 9, 10, 11, 12, 13, 14. Carry the 1, 3, 4, 5. 6.54 times 10 to the 6 meters is going to be our R for this problem. Is that good? I think that's a good skill. Be comfortable with working in those kind of numbers. So let's look on. What's the agent of centripetal force, you ask? No, you don't ask, because you know. It's the force gravity from the Earth. Force gravity, Newton's third law of force pair, isn't it? Newton's third law of force pair. Force on the satellite by the Earth equal and opposite to the force on the Earth by the satellite. So I'm just, you know that. How long will it take the satellite to make one complete revolution? So that's interesting, because you'll notice we're going to have to get velocity for that, aren't we? Because I'm just going to I'm going to use my equation holster. I want to find the time. I know period equals 2 pi r, the radius, over the velocity. And that's just rearranging, isn't it? Velocity is position change over time. We're just putting our period there. We also know the centripetal equation is velocity squared over r. So let's I'm going to move up here because I got room. Let's determine our velocity. If we have velocity, we've got radius, we can determine the period. I'm going to start with my equation. Centripetal acceleration, velocity squared over r. I'm solving for velocity, so centripetal acceleration times r, square root, because we want velocity. We don't want velocity squared. We want velocity. So we've got now, and I should have backed this up a little bit, square root 10 meters second times 6.54 times 10 to the 6 meters. And when we solve that, I get 8087 meters per second. There we go. So we want to find period now. Period is 2 pi r over v. We got v. We got r. Period is going to be 2 pi. Use your teammates, once you combine those distances, use that. A couple in the past, you've done this part right, and then you go back to a different radius. This is what you want. 6.54 times 10 to the 6 meters over the velocity 8087 meters per second is going to give us a period of 5082 seconds. And that's your answer. But we can do a little more than that. Let's talk, because how long is 5082 seconds? We'll divide by 60, get a minute. So maybe we can get our head around that. About 84.7 minutes. So 84.7 minutes. And that should sound reasonably familiar. We calculated the period of the International Space Station at about 92 minutes. And it's got a little, the radius is a little less because it's in that polar orbit. And again, Earth's that oblate sphere. But that's a reasonable period. So imagine that. Imagine going around the world every 90 minutes. That's what this satellite would do, and that's what the astronauts on the ISS are doing several times every day. It's good. Here's what I got for you for the weekend, or for the rest of today. Maybe, teammates, I'm not going to assign you anything the weekend. Recall, though, you got a Grande Fiesta coming up next week. So I wouldn't let those neurons you sharpened up all week go to sleep. Here's what I want you to do. I want you to take a shot at number 2. And I'll put this on the Schoology. I want you to solve number 2, A, B, C, and D. I will put the key up at 8 o'clock Monday morning so you can check it out. You're going to submit it to me on tomorrow, or about 8 o'clock Saturday morning, if you need that extra time. And I'll have that key up by 8 o'clock Monday morning. You can get a good look, and then next week's Grande Fiesta, you're in business. One change I'll make, and I'll send this on the Schoology. I don't know why I typed that. 5.98 times 10 to the 24th kilograms. I got a little crazy with the rounding, apparently, when I worked on it this summer. So 5.98 times 10 to the 24th kilograms. And teammates, let me show you this, because we're not going to do this. We've done those. We are good. We are good. We are done with this unit. I'm moving this into the space unit. Kepler's laws. And then this is all the new stuff we have for uniform circular motion and universal gravitation. We have come a long way, my teammates. We have indeed. I would also, this weekend, I'd pull out your workbook a little bit and flick through those questions we've done in the past. Your neurons are going to appreciate it. If you don't exercise them, your brain's going to prune them out. It's good. Send me a note if you got any questions, and we'll talk to you soon. Out here.